Okay, maybe we can start. So everything is good. I think you can see my slides. The recording is on. So, and everybody is there. See that Kaki, Alessandro are there. Okay, perfect. Well then, good morning. Welcome to this workshop, this EO4EU workshop, where we'll be presenting one of the use cases that we've been working on during this project. The use case is the sixth one, named the environmental pest. But first, I will make a quick introduction about the whole project and the agenda. So here's the agenda for the workshop. There will be the presentation of the EO4EU project for those that don't know what it corresponds to and our specific use case. Then there will be a technical presentation of my colleague Alessandro Grassi about the model that we developed. Then there will be an hands-on session on the EO4EU platform handled by my colleague Katja, and also like a quick presentation of the capabilities of the service that we are proposing through a notebook. And then there will be some perspective, future step of for the service, for the use case. And if you have any question, comments, we can set up a Q&A session at the right end. But don't hesitate to write down question during the workshop while we are presenting something that could be of interest for you, so that we can answer straight. I think it might be better to keep it fresh. So the project named EO4EU it's a quite large project because it corresponds to a consortium of 16 partners from 11 countries. It has this objective of developing a platform, AI augmented ecosystem for the Earth observation data with extended capabilities for user interface, for data visualization, map visualization, but also data exploitation. We'll go a bit more in detail in the capabilities, but the platform is the main project developed during this project. It will connect the existing major EU data, facilitating for the user to find it, access it, but also process it and work with the Earth observation data. It also has these capabilities of leveraging machine learning, cloud computing, and also having this platform that will be developed in the way that it's user friendly, including also virtual reality. So it's quite large with several capabilities. But the main objective is to bridge the gap between the complex Earth observation data, but also the big data from that to access it, but also to process it, and to bridge this gap and to make it accessible for any type of users. And that's the challenges that we are facing within the Earth observation data. We have like different source of information. It's all fragmented in different data centers. So the EO4EU platform has this objective to collect from the different point of sources and to put it in one single place. But it's also difficult to find and retrieve the relevant data when we are not especially expert in Earth observation. And if you don't know what data to use, you don't know also how to process it or to download it. And the EO4EU platform has this objective to collect the data, to put it in one single point, to also provide you with different services that will be presented later, the meaningful information about the data that you are seeing, and also to process it through quite easily with the user interface, but also with Jupyter notebooks for the more Python experts people. Who benefits from this platform? Many people can benefit from this platform. As I said, it's making it. It has this objective to make it user friendly, to facilitate the access of Earth observation. So even though you are not in the EO field, you can be interested in such platforms. So that's why there are many beneficiaries, such as the policymakers, the scientists, the private sector also, but also more expert people in the field, such as the EU data provider that can find really interest into that. And it can benefit really from the research to the private sector. So back to the use cases, to prove the capabilities of the EO4EU platform, 7 pilot use cases were developed. You can see the seventh one here. There are several workshops that are being organized in the next week. Some of them already happened, but if you are interested, please have a look at the EO4EU website to see the invitation for the other use cases. But in our case, with Systema, we made the focus on the use case 6, the environmental pest. And I desert locust pest is known as one of the world's most destructive migratory pests. A single swarm can travel up to 150 kilometers, have 80 million of locusts, and eat the same amount of 35,000 people. So we are facing really a major challenge that is highly impacted by the climate change, provoking increase of such crisis, and especially impacting countries that are already facing complex crises from conflict, social, but also environmental crisis. So it appeared for us as a really major challenge that we try to tackle and to try to provide meaningful information out of that to help the potential users that could be interested, from decision makers, but also to the single user, agricultural farmers, etc. So as I said, high priority global challenge. It has severe implications in socioeconomic for those vulnerable regions, but it's only when the desert locust, so in the biologic aspect, reach its gregarious form. Before that, the desert locusts are not a real threat, but when it reaches its gregarious form, it can group as swarms and be a real issue for the agricultural activities. This development point is strongly influenced by the climatic condition and the vegetation status. So we decided to find a way to use Earth observation, but also the climatic data to create a good monitoring solution. And also by adding contextual information and artificial intelligence, we ended up with an early warning system that will focus on the early stage of development of the desert locust in order to prevent the existence or the apparition of such crisis. To do so, we use contextual information, especially from what we consider as the reference right now in such field. The FAO Desert Locust Watch team produced a data set from 1989 to 2022, giving information about the desert locust at different stage and making also on-ground operations to identify the insects. And we see 4 main identification, which are the adults, the hopper, the band, and the swarms. And also inside the operation, we identified no locust, so no identification of the locust when they did it. But in our case, we made a focus on the hoppers and the bands, which are the early stage, so right before the gregarious form, right before the locust group up as swarms. We didn't really consider the no locust parameter because like for the entire data set, it was corresponding to a really small amount compared to the others. So it was leading to completely unbalanced data. And then with this contextual information, we had to link it with climatic information. So based on the scientific papers that we found and also the FAO guidelines, we identify 4 main parameters, 4 main climatic parameters that can impact that can influence the development of the desert locust, such as the temperature and especially the surface temperature, the precipitation, the soil moisture, and of course the vegetation, the amount of vegetation available. So with those, all those information, we ended up in a workflow that looks like this, like really simply combining all the climatic variable all around the Earth, and especially for the area of interest that goes from West Africa to Northwest India, identifying this locust occurrence from the reference FAO datasets and merging it into an AI model, a machine learning model, to identify not the presence of the locust, but to make a focus on potential ecosystem that will be suitable for the development of the desert locust. And like that, we have this early warning system indicating to decision makers, but also like to the control operation, where to go in the next days to identify the desert locust. But then I will let the floor to my colleague Alessandro for a more technical presentation. And thanks. If you have any question, don't hesitate to ask in the chat and I will answer.
Thank you, Max. So yeah, now I'm adding some information about the technical aspects of the model. Here I'm saying a few more words on the dataset we used. So as Max was saying, as input we use temperature, precipitation, soil moisture, and vegetation. Why we chose these variables? Let's say the most important one is soil moisture. We chose them because they correlate better with the ecosystem of the desert locust. For example, soil moisture is very important for desert locust to lay eggs, and also for the eggs to develop, because they need a moist soil to not dry up. Then temperature and precipitation are very important because they correlate with the time the eggs take to hatch. And vegetation, specifically we use NDVI, serves as a proxy for the amount of food available for the desert locust. The first three variables, we took them from EO5 land. Specifically, they have a hourly temporal resolution at their raw format, and 9 kilometer spatial resolution. While for the vegetation, which is NDVI, comes from MODIS, and it comes from with an 8 days temporal resolution at 5 kilometers, and it's available from the year 2000. While for the reference data, we have a presence-only dataset coming from the FAO, corresponding on desert locust findings. The FAO provides 4 different datasets that correspond to 4 different time at the 4 different period of the development of a desert locust. We focused only on the first 2, which are hoppers and bands, mostly because they do not have wings, so they do not move great distances. So when we find when we have a desert locust finding, we know that that desert locust has been there or around that area for a long period of time. While if we have a finding of an adult, it's hard to say if the desert locust just arrived there from a very far distant, very far location, or it was there for a long time period. And also hoppers and band being at the early stage of their life also correspond better on the position on where the eggs were present. And on the next slide, this is a screenshot of how the reference dataset looks like. So it's, as I was saying, is a presence-only dataset. So it corresponds only on findings of desert locusts. So there is we do not use desert locust absences because they're very scarce, and also they occur very close to desert locust findings, so they can't really be taken into account. Also, another thing that I wanted to show with this slide is how the data is distributed. As you can see, tend to follow roads, or in general sort of human infrastructure. So let's say the data is some sort of condition on where the humans can actually go and patrol and check for desert locust location. And then you can go to the next. So now start to talk a bit more about the methodology that we used. I have a couple of slides about the state of the art. So in general, this work falls in the field of study of species distribution modeling, SDM. which basically is a branch of science that tries to predict the geographical distribution of species based on environmental variables or climatic variables using satellites and climate models, as we did. And it has the peculiarity that often it works with presence-only data, so completely unbalanced data sets. So it was very useful to us to check this branch of science to solve our problem. And you can go to the next. Usually there are two solutions to work around the problem that the data sets are completely unbalanced. One is to use specific algorithm. The most common one is Maxent, which simply that doesn't need negative data, and it basically tries to fit a probability density distribution around the data that you have, with some mathematical constraints to do not have too many false positives, let's say, as it's shown in the figure. While another technique that is also found in the state of the art is the creation of pseudo absences. So artificially craft some negative data by, for example, drawing random points around the area under study and consider these random points as negative. In the beginning, we tried this technique, but then we found out that it wasn't really working well. So we focused on the Maxent approach, and we developed our version of Maxent that I will explain in the next slides. So first here a bit on how we prepare data to be fed into the model. So the model that we use take as input a time series where each time steps correspond to a 5 days average of the 4 variables that I explained before. So temperature, precipitation, soil moisture, and vegetation. In total, there are 10 time steps, and so in total, the model takes a time series corresponding to 50 days, each time step being 5 days average. And you can go to the next. Here I'm showing what the model gives as output. So the model takes as input this 50 days time series, and it outputs probability of presence corresponding to how suitable the ecosystem is, which is 7 days in advance. So there is a gap of 7 days between the last day of the last time step and the findings that we are using as reference to train the model. So the model always predicts 7 days in advance. And having this, and the model we use is, we call it RNN Maxent, which stands for Recurrent Neural Network Maxent, which is a custom version of Maxent that has the capability of looking at the temporal evolution of the variables. And in the next slide, I'm explaining a bit better what I mean by it. So the normal Maxent takes as input a flattened version of the time series if used as it is. So basically, at its core, it does a normal linear regression, and it doesn't distinguish between soil moisture, for example, at time step 1 and soil moisture at time step 2. It just treats them as two different variables, while and this is, of course, suboptimal because it doesn't reason on an evolution of the soil moisture itself, but it just sees, let's say, more soil moistures. And so it can't reason on how these variables develop through time, because it just takes the time series, it flattens it, and then it applies a linear regression to it, and then some other math to make the algorithm work. But it is as simple as that. While I can go to the next. What we did is to apply in between this flattening a recurrent neural network. Specifically, we use the GRU. So basically here, I'm showing what happens inside the neural network. Basically, the model takes the 4 variables separated by each. It takes each time steps separately. So first, it takes the first time steps. It makes some reasoning, and then it takes the second time steps and makes some reasoning and goes on like this. And so it knows that there is always, for example, soil moisture being given to it. It's just the same variable at a different time step. So it can reason on how this variable evolved. And then you can go to the next. So the output then of the recurrent neural network will be still a flat vector, but this time will not be a vector of the input variable, will be a vector of a so-called hidden representation of the variables that is given by the network. So somehow the networks learn to create this flat vector, taking into account the temporal evolution, and then the linear regression is applied to it, and that from now on it's equivalent to Maxent. This was a bit more technical part. Okay, now on the result aspect of the work. As you can see on the image on the left, the area that we worked on is quite big. This is the area corresponding to the availability of desert locus findings from the FAO. So we use the whole area they operate on, which spans from West Africa to India. And on the right, you can see how the output looks like. It's a suitability index. So it's a value between 0 and 1, but we just take the values above 0.9 to make sure to not overpredict the suitability of the desert locust. Otherwise, we would have two big areas. And so basically, we trade off. We try to gain more precision at the cost of not predicting maybe some areas, but at least we're sure that what we're showing is actually areas that have high probability of finding desert locust there, because the ecosystem was good in the previous 50 days. You can go to the next. Yes, so some details on how the model works at inference time. The output of the model is it's quite lightweight. It's 5 km resolution, so it's 6.24 megabytes for generating the whole image. It takes around 1 minute to compute, and it takes and also no GPU is needed, so it can work with no problem also on the CPU. So there's no specific hardware that has to be used, and yeah. You can go to the next. So how did we validate the model? First of all, we split the data between, we took the data from 2000 to 2019 for training, and data from 2020 and 2021 for validation. So we had a split based on time. So to make sure to not have some sort of spatial correlation between the feature, because we didn't want to have between the desert locust findings. Sorry, we didn't want to have a finding used for training and a find used to validation being very close in time and space. So we just divided it by time, so to make sure that they do not correlate. And we did two different types of validation. So being the reference dataset only positive, so only desert locus findings, it's hard to compute. Actually, it's impossible to compute normal scores like accuracy, precision, or F1 with actual reference data. So we divided it in two. We had first we compute some scores that can be computed only with desert locus findings. So we have a recall of 0.30, which means that 30% of the desert locust finding in the validation set are actually recognized as findings. And on average, the area that is predicted as positive overall, the whole area that we're taking into account, is 1.1%. Here a note on the recall that is 30%. This is because, as I was saying before, we use a threshold of 0.9. So it's very, let's say, strict threshold, and so we are able to recognize 30% of the findings, but predicting only just 1% of the area. So we have very targeted output, let's say. Then another way that we validate the model was to draw random points and see how the model can distinguish between a point that is actually a desert locus presence and a point that is just a random location in the map. So with this, and also we took 3 times more random points than findings. So there's much more random locations. And on this technique, we have an accuracy of 78%. Precision is 83. So the model is quite precise, and recall, of course, is the same, is 0.30. You can go to the next. I'm showing some maps. So here is a result zoomed on Morocco for the 21st of May 2025. As you can see, the model was really close to get it right. To be fair, on those points, the probability, if you check only on those points, the probability that was predicted by the model was above 0.7. So still, but since we are considering only 0.9, they didn't fall in our prediction. But still, the model got really close to them. And also, if you zoom on those points, you can see that they are exactly by some roads or some fields. So we can say that if the desert locusts weren't on those points, most probably there's good chance that the model predicted well to highlight an area that is just 20 kilometers away from those points. So yeah, I wanted to show this image to see how also complicated it can be to assess how well the model is doing. On the next slide, I'm showing another example over. Yeah.
If I can add just something about this example, is just like also a good way to show that the operations that are happening to find the locust, or actually to not find the locust, is made at a specific time, at a specific moment in the day. But it doesn't mean that if they found locust like at several kilometers, you don't have especially locust on the area above, because there is no enough distance to really say, okay, if there is locust there, it means that there is no locust to 5 kilometers north.
Exactly. So yeah, here another example. So I'm showing the area of Saudi Arabia, where here the model did much better. So it highlighted exactly where the desert locusts were present. But by the way, this is the same day as before, just moved over Saudi Arabia. And also I wanted to see how also there's no other findings in the whole region that I'm showing in the image on the left. And there is no findings reported by the FAO, and the model didn't predict anywhere else apart from the tip of Somalia, where, by the way, it's a location where desert locusts tend to occur very often. Here we didn't have neither findings and neither reported absences, so we can't really say what was happening there. But our models highlights a very high probability of finding desert locusts there. But overall, we can say that the model here was really precise in predicting the high suitability over this area of Saudi Arabia. And I think this was the last slide from my side.
Yes. And I would like to add also this example with Somalia here is the fact that this is ground control, so it's like man-made operation to identify the desert locust, but the operations are really impacted about the conflicts that can happen in some specific countries. Somalia is known for having some conflicts. Yemen also, as you can notice, we identify some area that are suitable. don't see the pointer, but we identified some areas that were suitable for the desert locust in Yemen, but no locust findings in those areas. So the man-made operations are really dependent on the capabilities of the operations to happen in the countries. So that's adding complexity in the entire model to really predict and to really validate the prediction that we are making. Yeah. So thanks Alessandro for the technical presentation. If you have any questions, don't hesitate. We're pleased to answer. And so the service that we develop and that we just presented, like the overall model, has been integrated into the EO4EU platform. And here is the workflow, or it was integrated. I will make a quite quick presentation about this workflow to introduce also the hands-on session that Kakia, my colleague Kakia, will be doing. But basically, it happens like that. So the way to use the model on the platforms goes from through three main services on the platform. First is corresponding to a dataset search that is performed by a knowledge graph. So you indicate area of interest, time range, and then you search inside the knowledge graph the data that you are interested in. We made it quite easy, easy to use, so that the users that don't know, for instance, the exact name of the satellites can search more for the variable than the sensor itself. So if you don't know about ERA5 length to identify surface temperature, precipitation, soil moisture, the knowledge graph has the objective to indicate you the right sensor if you are looking for precipitation or humidity or whatever, and it gives you the capability to collect the data. The knowledge graph is providing you the meaningful data that you are searching for. And then when you define the area of interest and the time range, it produces a Python script that will collect the data on a platform named Adam, so the Adam platform, and then you can collect all the data that you need. And then we go inside the workflow. So you select the data that you want, and you can produce your workflow. You can edit your workflow, and so the use case 6 was integrated into the platform. As you can see here, this is the workflow that you can generate on the platform. So it's quite simple. It's just blocks that you push inside the graph, and then you connect to each other. There are tutorials on the platforms, so to know which steps to follow in order to run the model that we created, and then you can obtain your data output into different types. For the customer phase, it's like the map visualization and the AR version of it. Here is like a quick explanation of the model, but you just add it. And then when the workflow is finished and run, and when the run was complete, you can visualize the output that you have directly on the platform. And here is an example through the VR visualization, where you have on the right the legend showing the values. So the values here are going from 0 to 1. So you have the full capability of the model, the full level of confidence, and then you can spot through the VR the area that were impacted. But then I will let the floor to my colleague Kakia for an hands-on session on the platform.
Hello everyone, and may I share my screen?
Sure, I'll stop sharing mine.
Yeah. Okay. Thank you all for the presentation. What we would like to present, as my colleagues explained, Alessandro were presenting, was a EO4EU platform. What you can see is, as we are saying, a one-stop shop of all the data sources that you can find from Sentinel Hub, and it was a quite challenging task. As we understand, we have a lot of challenges through the harmonization of data, the different APIs that all the Sentinels and the Earth observation providers are creating, different, if you can say, ways to download data through APIs, through different accounts. So all these are harmonized under EO4EU platform. What you can do is following the link that we're going to add you in the chat, and you can create an account. What is going to be needed from you is just your first name, last name, email, username, and password. And this can register you in the EO4EU platform. From my point of view, I can enter, sorry, I was, had a lot of login, I'm sorry. Okay. So what you're going to see is the dashboard that was already presented in the presentations. What you can see here is the home page and our, if you can say, our three main components that you can do inside this platform. The first thing is that you can search all the data sources. You can select either some keywords, or you can select a specific data source that you would like to search. For example, in our case, for use case 6, you can search with ERA5 and temperature, for example, and then temperature. And then you're going to get 50 data sets that can get you upon the results of ERA5 or from different data sources. And you can select whatever is more convenient to you. You can check, for example, here the descriptions of what is the specific dataset. What I would like to show you is that you can also select a specific area of interest. In our case, for use case 6, for example, you can create a polygon here in order to select this specific area in order as an area of interest. And of course, you can select a specific date range. For example, a date range of 2, 3, 4 days, 5 days, or whatever you want. What you can do next is that you can filter the output. This means that all the process, what is going back to the API, to this ERA5 provider, or to other providers, they can send you, for example, the products that are created, and you can download it inside our ecosystems. We don't provide only the easiness in order to access and download data, but we also provide all the infrastructure in order to process this data, to download data in a specific cluster, dynamic cluster, and then make some processing, not in your local PC, if you can say, but in a more advanced, with more advanced of resources. So you can select, for example, all the products that are created, generate a script. This creates a download script inside our, if you can say, processing and downloading component, and then you can save this dataset. As you can see also, you can select manually, because there was also a request from the users from previous use cases that, okay, I can select an area of interest, but probably I want to create a polygon here with longitude and latitude that's quite specific, and it's quite, if you can say, transferable also to other data sets. This is also a case. You can manually enter your specific points in order to create a specific polygon, or you can select from previous searches and selection a polygon that is already for your case. For example, I can select, for example, from Modis. I searched also already a Modis dataset, and I created this specific polygon. So because there were many requests that, okay, I can have multiple data sets. I don't know if I'm quite, if you can say in details about the polygon that I want to select, or I want to replicate my geospatial selections to other data sets. So this is also an option. So we can set data sets. Another thing is that you can select, for example, datasets in order to be downloaded in our premises, or you want to download it through the use of the use cases. Just for an example, I can create a test workflow. I'm just entering a name, and I'm selecting, for example, data that I have already set and saved as from the previous step. All the data sets, as you can imagine, they have a specific, if you can say, selection in time range, and more specifically also in space. You can download the whole world if it's possible, but usually they're having a geospatial, if you can say, selection in a specific date range. And what you can create in the workflow editor, you are going to see a drafted workflow. In our, if you can say, in our definitions in EO4EU platform, a workflow is a chain of action. So a specific chain of action is creating a specific workflow. So as a user, what is the most, if you can say, easy workflow in order to create? Just you add the data sources. When we're meaning data sources, we're discussing about the data that you have selected in the previous step in order to be downloaded, a data output, and of course, if you like, the visualization capabilities of the platform or the use of AR/XR. This AR/XR component creates a digital elevation model for your output. If your output is a geospatial image, like a JPEG or not JPEG, TIFF, for example, and this can be presented in a map. So the most simple, if you can say, workflow is to create a data source, a data output, customer face, and AR/XR. May I add also my data as in situ? When I mean in situ, may I add also my own data from my PC in order to enhance this processing? The answer is yes. You can upload your own, if you can say, data source as a zip in order to be uploaded in the platform. So together with your own capabilities, you can add also your own data. Another thing that I would like to demonstrate for presentation premises is that you can also add a Jupyter notebook. When I'm meaning a Jupyter notebook, you can add your own, you can upload your own, if you can say, Python. You can drag and drop your own Python in order to make the processing of your own needs. Probably we are having right now models like merging rasters, geospatial resolutions, the output of use case. Yes.
So I think the screen is locked, or I don't know if you changed to show the
I'm
Jupyter
sorry,
notebook.
I don't know, because of the heat. I apologize. Because of the heat, I'm working from home, and my internet connection has a lot of disruption. So probably
we'll turn off the cameras.
I'm free.
So
I will close my camera. Okay. Do you see now my screen?
Yeah, perfect.
Okay, thank you. I'm sorry about that. So you can upload your own Jupyter notebook with a drag and drop. This is a way in order for a user that is he has his own, if you can say, needs of coding. He has his own, if you can say, processing capabilities, that he can upload his own code in order to process the data. So in this way, you can also add a Jupyter notebook. And of course, as Maximilian says, all these are connected, of course, in order to show you. And what you can only go and check is just save and publish. I'm not going to save and publish because I have nothing in my this specific workflow. So this is the EO4EU, if you can say, the use of platform. Another useful thing is the user guide. Here we are having all the descriptions of all, if you can say, the steps that you have to follow. And here you can see also per use case specific information about how you can run and your specific workflow. Another thing is, of course, the data visualization. The data visualization, when we're talking about data visualizations, we are discussing about, for example, I don't know if we are having something here, is about CSVs, is workflows that we're talking about numbers and how we are creating graphs. Map visualization is about how you are demonstrating TIFFs. File Explorer is what you are having inside your specific workflow. Excuse me. For example, here in use case update, I'm having, you can check all the data that have been downloaded on a map. Map visualization, for example, I can demonstrate something that is downloading the whole world, for example, that because of ERA 5, and how you can merge the input. Here is the processing my whole world because I didn't add a specific area of interest. And XR VR, probably, I don't know. I'm going to show you also in a presentation. I'm sorry because I'm having a lot of disconnections, and I apologize about that. So what is EO4EU, as I said, and just a wrap up, is a user probably can use EO4EU platform in order to search data sources, to select different data sources, to create a specific chain of actions, use predefined functions, and start a workflow. Another thing is to enter the platform, upload his own dataset as in situ data, together with other data sources, creates a workflow and starts a workflow. Or he can create his own notebook through FAS, through function as a service, and to run his own processing capabilities. Another thing is that probably you can also, we can show through the notebooks that you can use EO4EU as an API. You are an expert as a data, you are an expert user for Earth observation data. So probably you just want to log in to the API externally. You can select your own datasets, you are creating your chain of actions, and you would like to run again and again your specific workflow as a cron job and get the results. This is also the case for use case 6, because we are having needs of these 50 days that we would like also to provide to the users as a data set of 50 days processed for the specific, if you can say, use case that can be found in our knowledge graph. So our knowledge graph doesn't have only the data coming from the Sentinel and Earth observation, but he can have also useful data sets from the users that they would like to be provided in a public way. This is also the case in order to have and to extend our knowledge graph. For example, for the Eurostat that we are having for use case 3, it was a data source that was not implemented. It was not in the starting days of the project to be integrated inside our platform, but because of the needs of the users, we added as an external, all the users can make a request to extend this data set in our knowledge graph. So all these things are putting together under our platform. And this is the knowledge graph. as we are presented about the notebook. I think about the notebook is going to be presented afterwards also from Maximilian and the output. What I would like to show also is the VR, that is, as I said, the digital elevation model that you are going to see through our platform. And here is also a presentation of the virtual reality, that the same output of the virtual reality and the augmented reality of the digital elevation models can be selected through an application of in the Oculus Meta Quest, and you can check, for example, this is the fire risk of an area in real time in your glasses, that you can make a zoom in, zoom out, you can process, you can take this data and move it in the space. You can have, for example, other works, and you can EO4EU provide you this digital elevation model and the fire risk propagation in real time. Or you can use also our augmented reality for as a mobile application, and if the data are provided in close to the house, if you can say in a scale close to the house, you can also check your, if you can say something from the map in front of your camera. This specific tip that was uploaded, it was in a scale of a town, so it was quite, you're having quite small pixels dedicated to you. And this is my presentation about EO4EU. I'm having questions. I think, Maximilian, I don't know if you can also show the VR output, because I'm having difficulties from my connection here.
I didn't open it yet. I mean, I didn't open it, but maybe
okay.
maybe I can, if I open it and it loads fast, I can show it later.
Thank you.
Thanks, Kakia. And so I will share my screen again so that you can see the right one. Wait. Let's. Yeah, I think you can see my screen right now, and you can actually see the Jupyter notebook. It's just to show, like, so there's this, so Kakia made the presentation of the user interface, so to have like this user-friendly platform so that you can collect data when you are not aware of how it works properly, and you can process data with easy elements directly on the platform. But you can also run it through through Jupyter notebooks if you are a bit more aware with Python scripts and also like the machine learning itself. But basically, I will not run it to make it faster, but you have the cell outputs to see how it goes. Basically, you download the meaningful package to run the overall model, and especially this Triton client to look for the model. So the model are all stored in an efferent server that you see here, so that you have the link, and you can just grab the model directly from the server, and with a simple function here that you can get the results out of the model. So basically, we will provide the data that you collected for the specific date that you want the output, and then you provide the data. It goes inside the server. The server made the run of the model. As the model is quite lightweight, it's quite fast to run it on the server, and then you will get the whole results. So the first step is of course to get the input data. So as I was saying, and as it was shown also on the platform, we collect it through the Adam API and the Adam platform, so where you can find the meaningful data. So here it was the MODIS data for the NDVI. You collect the dates that you want, and then you can load as soon as you have everything, you can load through the different folders where you have the data, and generate the input sequence corresponding to the 10 time steps with the variables and the size of the area of interest. And then inside the server, you can run the inference and obtain the results for the exact date that you selected. So we made an example for yesterday to show it. And unfortunately or fortunately, the prediction was quite light. As you can see, there was a few areas that were considered as suitable for the desert locust. Unfortunately for us, there is not much to show. Fortunately, it means that there is no major event or crisis that can happen in the next days in those areas. And so back to the slides. I will come back a bit more on the perspective of the work from what we have presented since the beginning of this workshop. We made some additional validation compared to what Alessandro presented, thanks to ICP, the International Center of Insect Physiology and Ecology. We made the validation work from January to March 2023 with 650 records. But as you have seen during the presentation of the results, there is really a complexity to really say that the output is matching well with the presence of the locust, the occurrence of the locust, or the non-occurrence of the desert locust. So the results that we obtained from this validation was less favorable than anticipated. But we found meaningful insight on the data and also on the complex task that we are performing. And so there was like a lot of key areas of improvement. So the next steps for our work, also related to the EO4EU project. So for the service itself, we have to redefine the variables. We were using the NDVI as variable to estimate the vegetation, but we might consider other variables such as the greenness index, which is more like optical identification of the vegetative areas in order to better define this variable for the desert locust, because we figure out that there was some mistake happening in the estimation of the vegetation through the NDVI and especially through the MODIS sensor for this specific index. Then we are considering refining the model for higher prediction with higher resolution. As Alessandro was showing, we are considering this threshold at 0.9 to 1 because we want to focus more on the 90% where we are the most confident to make sure that when we are giving this information to potential decision maker, we are not leading them to some areas where we are not extremely confident that it's suitable for the desert locust. So we have to refine the model in order to go in that direction and to reach as much as possible what the FAO is providing with ground control operation, which is like exact coordinate of where we could have potential locust. Then we would like to enhance the forecast capabilities. Right now we are providing 7 days in advance within the last data available. And we would like to increase those capabilities by ingesting new climatic models, by actually working on forecasts so that we can predict several days in advance, more than 7 days, like maybe considering 1, 2, potentially 3 weeks, and maybe also really long term and making prediction with climatic scenarios. So for the next 100 years, estimating areas that could be impacted by the desert locust. As Katja was presenting into the slides, and was presenting into the slides, we are also considering setting up a cron job inside the platform, but also for the service itself for permanent prediction, because this specific task, this specific service has for objective to produce data constantly every day to have like constant monitoring of the desert locust, and not especially like collecting specific data at specific dates to have only one day. The idea is to have constant production so that you can build reports, you can build weekly averages, monthly averages, and defining really the area that are at risk. We are also considering application to new species. The methodology that we presented is the Maxent methodology presented is a classical one in the species analysis, species prediction. So the one that we developed within with RNN and Maxent could be applied to new species if we have the main reference data to train a new model. But that's the idea, to have like maybe general model that can select the species to monitor and can provide meaningful information for different species, ones that are environmental for environmental plague, but also potentially for health issues with the vector-borne disease. So that's the idea for the main service here that you see with the main early warning service. We are also developing new services to build a full chain of monitoring of the insects. And we are extending from the early warning, identifying the suitable ecosystem, we are extending to the swarm prediction. Here, the idea is to follow the swarms. So if the early warning didn't work well and we couldn't prevent properly a crisis for many reasons, it could be for extreme environmental event that we cannot predict, or also, as it happened in 2020, there was the conflict and the COVID at the same time in some areas over Yemen, so they didn't have the capabilities to manage the desert locust, so it became into huge swarms, and then the crisis is already happening. So the main objective of this part of the service is to produce meaningful data while the crisis is happening, to know which area will be impacted in the future days. So it works a bit the same than previous service, but here we are working with a stochastic model. We are having the same input variables, so the wind for the movement, the temperature, but also the vegetation with the leaf area index, some guidelines about the locust biology, and the first model outputs with the probability of the suitable ecosystem, the probability at the end of the presence of early stage desert locust. And then there are weekly runs that are happening with 10 to 20 week scenarios based on the biology of the locust, and various movement patterns that are happening in the stochastic model. And as you can see here, you have the different scenarios with the different position of the desert locust happening, and we have different time steps, and at the end we can provide probability of the swarm at specific areas, but also information about the swarm size. Because as you have different location of the locust, you also have groups that can merge together and produce larger swarms. Then, sorry. So, and then one last perspective or service that we would like to develop is an impact assessment. So we have this early warning, we have the crisis monitoring, and then if the crisis happened, we want to measure the impact it had on the area that were touched by the desert locust. And for that, it can provide meaningful information for agricultural monitoring, but also estimation of efficiency. And the idea is to make temporal analysis over the agricultural fields to identify rapid changes. And by identifying these rapid changes, we can identify the impact due to the desert locust and to estimate it. And this was my last slide. I hope it was of interest for you. And if you have any question, any comments, anything, don't hesitate to write it down in the chat, or just to open the mic and we can have a chat. And thank you all for joining this workshop. And yes, Kakia just shared in the chat the link for accessing the dashboard, but also the email for the technical support if you want to try on your own the platform and try the capabilities to run run this use case 6 for the desert locust, but also you can try for the other use cases that are for many other applications. Right? Yes. No. I thought there was a question. If there is no question, then I can free you from this workshop quite earlier than before. I don't know if anyone wants to add something. Christina, I don't know if you want to add something.
No. A very big applause for the presentations. Thank you. It was very, very detailed. Everything. Thank you so much.
Sorry, the headset was off, so I didn't hear.
Yeah.
Sorry.
Thank you very much for your presentations. That's
Thanks.
Maximilian, we can arrange afterwards for the registered users in order to send them the notebook, probably to help them with any technical support. I have already in the chat added the website of the EO4EU platform, our email of the technical support that we can answer questions. And if someone wants, we can also go deeper in the notebook that were presented or in the platform. I don't know if they have any specific questions, or do you want to make a registration together?
All right. Sorry, should I say something? No. I didn't understand the final.
Okay.
Thank you, Bako, for joining the workshop. Sure, yeah, we will try to share as much as possible the availability of the model. We have ideas maybe of producing some data and sharing it with the public. I believe that could be good. If you are interested into the desert locust modeling and the work, I leave my professional email so that you can contact me, so we can get in touch for this specific service. If you want a deeper presentation of the model itself. And yeah, all right. Then thank you all for joining, and don't hesitate to look on the EO4EU website for other use case workshop that will happen in the next days, and see you around if you are interested in the topic of desert locust or in general environmental pest and species prediction. Thank you. Bye-bye. Ciao, ciao.
Thank you all.
Bye.
Thank you.
Bye.
Bye-bye.
Thank you. Bye-bye.
Bye.